So this is from 2007. You see this FRQ number 2. So anything that is within 1 and 2 will be calculator active. And then let's see. Calculator active for numbers 1 and 2, and the ranges are going to be non-calculator. Okay, so you can have your calculator for this one here. Particle moves along the x-axis, so that's velocity v at time t greater than or equal to 0 is given by v of t equals sine of t squared. Again, make sure that whenever you're using your calculator on the AP exam, that you're always in radian mode. It's really going to be important, especially anything dealing with trig. Anything dealing with trig, you want to make sure you're in radian mode and never in degree mode. That's for the entire AP exam. Okay, pretty much for this calculator. We're pretty much never in degree mode. Okay, graph of V is shown, and we see that t sits between 0 and √5 pi. Position of the particle at time t is x of t, and position at time t equals 0, x of 0 equals 5. This is it gives you a starting point or a given point. Okay, so part A says find the acceleration of the particle at time t equals 3. We could work it out by hand, but this is calculator questions, so we can simply do b prime of 3, which is the same thing as a of 3, and then we can just make our calculator do the work for us, right? We can enter the sine of t squared, do the math 8 and derivative feature, or you can work it out by hand. If you want to work it out by hand, it will be cosine of t squared times 2t. But you don't have to because this is calculator. Okay, so our acceleration is negative 5.467 or 5.466. We're just going to round to 3 decimal places. Okay, if you want to work it out by hand, you'll be able to get the same thing as well. But this is perfectly fine, since with the calculator section, they're not expecting you to work it out by hand. Okay, part B, find the total distance traveled by the particle in the time interval from 0 to 3. Total distance, what's the formula there for total distance? We have to involve what? Definitely integral, but the fact that total distance, we only want, right, rather than displacement, where we're keeping track of all the positive and negatives, we only want everything being positive. So how do we get that to happen? Absolute value. Yep. So the integral of v of t with absolute values or with absolute value around it. Okay. Math 9. Now I can find the absolute value under math number ABS, but I think there's another place that you can find it. Is it alpha? No. There's a shortcut menu. Yeah, alpha function, alpha window. If you go to alpha window, there's an ABS feature there. If that's any faster, or you can just do math number, but there's multiple ways that you can find that ABS. Type in your velocity function. it takes a while for the absolute value. Okay, 1.702. Find the position of the particle at time t equals 3. Well, we have the original position, or we have a given position, and we also have a velocity function. So we can use our formula here, right? Final position equals initial plus displacement, right? You use this formula to, like, a lot of times with particle motion, this formula comes up a lot, right? That final equals initial plus displacement. So I want to look for my position at 3. I have my position at 0, and I just want to figure out how much change has occurred or how much displacement has occurred in that time interval. So this time displacement is without the absolute value bar, right? Now, I just want to point something out here. The total distance is different than the displacement. What does that tell you about this particle? Yeah, it does change direction, right? So if this object never changes direction, it's only going either to the right or going to the left, these values will always be the same. Total distance and displacement. They're only going to be different if this object actually travels, goes backwards, changes direction somewhere in between. So as soon as that object changes direction, their displacement is always going to be less than the distance in that time interval. Okay, part D, between 0 and 5 and root 5 pi, find the time at which the particle is furthest to the right. So this is basically applying EBT, right? You want to find basically the largest value, positive value, right? Largest positive value. Because the largest negative value will be furthest to the left. So we do want to find critical points. We can definitely use our calculator and find these x-intercepts. Okay. Another way that you can do this is you can do this by hand, because if I do sine of t squared, looking for where sine of t squared is equal to 0, right? This is my velocity function. I can do this. I can set sine of t squared is equal to 0. If I do inverse sine, basically using unit circle knowledge here, where is sine equal to 0? Sine is equal to 0 at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. All right? And if I take the square roots, then these are all the values that show up on my critical point. Now, you can definitely use your calculator and use second trace. You can use 0 and find each of them separately, but sometimes it's even a little bit faster to, if you know your unit circle values, just work it through, and then you can make your sine line. And if I have my velocity sine line in front of me, I know it's going to be positive, negative, positive, negative, positive. the furthest to the right is going to be where quote unquote max is going to occur, right? So I know I only have to test root pi, test root 3 pi, and endpoints. Right? Don't have to worry about root 2 pi and root 4 pi because those are change in direction where we're going left and then we're going to the right. So this is furthest left. We don't care about furthest left, just furthest right. So we need to find each of the we need to go through this final equals initial plus displacement for each of the points. We already know what x of 0 is, but we need to find it for root pi, root 3 pi, and for root 5 pi. So x of 0 equals 5. X of root pi is just initial plus displacement. So enter that in the calculator. Root 3 pi is from 0 to, this should be root 3 pi, not root pi. And then from 0 to root 5 pi. And then we just compare each of those 4 values, see which one is the furthest to the right. And the furthest to the right is going to be that root pi. Double check that again. Again, the most important information is that, oh, sorry, this is the case where it says find the time. So the more important information is here at time t equals root pi. Usually, the problem will be asking for that value where that maximum, where that furthest to the right occurs, but this time it's asking for the time. So t equals root pi, and we're determining that based off of the fact that furthest to the right is 5.895. Hopefully we've done extreme value theorem enough where you feel like there's a pattern to how these problems are set up and recognizing it and applying it. Okay, next page. Okay, velocity of the particle moving along the x-axis is modeled by a differentiable function. Again, that just means a smooth curve, no sharp turns. Where position x is measured in meters, time t is measured in seconds. Select values of v of t are given. Particle is at position x 7 meters when t equals 0 seconds. So we can create some we can say that x of 0 equals 7 as a way of representing that in a more compact form. Okay, estimate the acceleration of the particle at t equals 36 seconds. It doesn't ask us to find the exact value, it just asks us to estimate the acceleration. We have a table where at specific moments in time, they give us velocity. So how can we use the velocity table to help us estimate acceleration? Find a slope, yeah. So acceleration is the derivative of velocity, another word for derivative is slope. So what order pairs are we forced to have to use here? 30 and 40, right? Because those are the closest order pairs. We don't have a choice here. Now, if it says if it said t equals 32, then if it lands directly at that point, then we have some options. You can choose these two or these two, but 36 is exactly between 32 and 40, so we have to use that. And what's our unit of measure going to be after we find the slope? Meters per second, right? So I think we're pretty good understanding that there's a change in units whenever we do a derivative. We also have to understand that if you take the antiderivative, there's also a change in units. So I'll make sure that we understand that both ways. Okay, so part A. So we know that the change in velocity over this time period is 11/8 meters per second squared. Okay, using correct units, explain the meaning of the depth interval from 20 to 40 of v of t dt. I think it's easier to express this if we go through first theorem, right? So just notation-wise, what would this look like as first theorem? You know, integral of v of t turns into what? What's above velocity? Position, right? So position, you can use x or you can use s. I typically use x for particle motion. So once I get to x, I can plug in upper and lower bounds. So x of 40 minus x of 20. So this feels a little bit more concrete. What does this mean? How can we represent that in words? Change in position of this particle in these 20 seconds. Oh, we're not done with part B yet. Use trapezoid sum with 3 subintervals indicated by the data to approximate the depth integral from 20 to 40 of v of t dt. So 20 to 40, we want 3 subintervals. So find the width. So subtract each of the t values to get the width, and then your formula is 1/2 width, height 1 plus height 2. Okay, try that and use your calculator. See what you get. Okay, part B. So we want to hold on to all the negative values because we're not asking for total distance, we're just asking for displacement here. So it's okay if you have negative displacement. That just means that in that 20 seconds or 20 to 40, this particle is going to change position in a negative direction. So we know that what this negative 75 meters tells us is that if you compare this particle's position between 20 and 40, by the time he reaches 40 seconds, he's going to be 75 meters to the left of where he was at t equals 20. Okay. Part C, between 0 and 40, must the particle change direction in any of the subintervals indicated by the data in the table? If so, identify the subinterval and explain your reasoning. Okay, so looking at the velocity sign line, or sorry, velocity table, can you indicate the number of times, the least number of times that the particle has to change direction? 2, okay, and then why would you say 2? Good. So we see a change in sign between 8 and 20, right? So this is basically kind of like IVT because we know it's continuous function that it can't skip over 0, right? It's got to, well, in order to get from 5 to negative 10, it's got to change direction to turn around. And then where's the other interval? From t 32 to 40, right? There's another change in sign here. So this particle was moving left, then at some point in time, it's going to turn around and move to the right because there's a change in sign. So really don't have to indicate much in terms of identifying a theorem, just have to be able to kind of reason out the fact that a change in sign for velocity means a change in direction. Because we see a change in sign, we can narrow it down to these two subintervals. We don't know exactly the moment in time where it changes direction, but we know it has to occur in these time intervals, and this is the best we can do because of the limited data we have. Okay. Questions with part C? Okay, part B. And usually on FRQs, part D is a little bit more challenging. But and you get to an FRQ on the AP exam, really you're just trying to, if you can get A, B, and C, or get parts of A, B, and C, that's good. And so you never want to stress out if you can't get the last part of an FRQ. You just want to be able to get enough to earn some points. You want to get perfect on every FRQ to do well on the AP exam. But just let's talk about part D here. It said, suppose that the acceleration of the particle is positive between 0 and 8 seconds. So if my acceleration is positive, what does that mean about my velocity? My velocity is always what? Can my velocity dip to 2 and 1 in this time interval? It has to always be what? Increasing, yeah, because acceleration, the positive acceleration means my velocity is always increasing, right? So I know that between 3 and 5, or between 0 and 8, my velocity is going to be at worst 3, but then it's going to continue rising up to 5. So it's always going to be increasing. There's not going to be any sudden movements that we don't expect. So it's going to be 3, 3.1, 3.4, and on until it reaches 5. But it's never going to dip below 3. It's never going to dip. It's not going to ever jump above 5 and come down to 5. So it's going to be a slow, gradual increase, right? So we know that to be the case. So we kind of just visualize what that looks like, right? So if I have my velocity graph, I know that at 0 seconds, it's 3. And then at 5 seconds, sorry, at 8 seconds, it's going to be up here at 5. All right, my velocity graph is going to be looking like this. It's going to be a slow and steady increase. Okay. Now it says, so we kind of have an idea how our velocity graph is going to look. It's going to go from 3 to 5 in that 8-second interval. Explain why the position of the particle at t equals 8 seconds must be greater than 30 meters. Okay. So worst case scenario, let's just figure out what is the area under this velocity graph, right? We know that area under the velocity graph is going to be displacement, right? That's going to tell us how much change in position is going to occur. So we know it's going to be more than this rectangular box here, but let's just do worst case scenario, right? Let's say that, at the very least, we don't know what this region is, but we know it's got to be greater than whatever this region is. What is the area of this box? 24, right? So let's think about our position function, our locating position. So worst case scenario, if I want to find my position at 8 seconds, I can start off with my position at 0 seconds and then figure out how much displacement is occurring in that time interval. So x of 0 is 7, right? That's given to me here, 7. 7 plus 24 is what? 31. But I know that my position will be more than 31, right? Because there's some extra space here that we're not accounting for, and we don't have a formula for it, but we do know it's more than whatever we have in this box. So explain why the position of the particle at t equals 8 seconds must be greater than 30 meters. Okay. And we know it has to be greater than or equal to 31 because we know that our velocity is always increasing and that the area under this velocity graph is at worst 31 and obviously more than 31. Okay, so since x of 8 is greater than or equal to 31, then we know for sure that our position is greater than 30 since positive acceleration guarantees the velocity will never fall below v of t equals 3, right? That positive velocity is guaranteeing that my velocity graph is always rising, and I know the area under the velocity is my displacement. And my worst case scenario is better than what my restriction is. So Okay, let's start into our homework. We still have, doing another 5 minutes or so. So page 5. All right, the more we do in class, the less you have to do for homework. Okay, so hopefully you guys feel that the more you see, the more comfortable you are, because a lot of these problems just feel like different variations of the previous ones. Okay, let f be the function that's twice differentiable. Again, smooth curve. Table gives values of f for selected points in the closed interval from 2 to 13. Estimate f prime of 4. We know derivative is related to slope. You're forced to have to use which order pairs here? 3, 5, right? There's no other options. You got to use those two. Estimation, so you can use a squiggly line to indicate we don't know the exact slope, but we can estimate based off of the data that is provided. So change in y over change in x. They didn't provide any units, so we don't have to indicate any units. Okay, part B, find the depth integral from 2 to 13 of 3 minus 5 f prime of x. Okay. How would you begin this problem to make it maybe easier to interpret? Good. Let's split it into two, okay? See that there's a minus sign here that allows us to completely separate these two. These are basically unrelated. Whatever we do to this one is not going to impact this one. They're not connected by multiplication or division, so we don't have to really treat them as individual things. So once we separate them, what strategy would you use to take care of the antiderivative of 3? What rule? How? Okay, that's power. For f prime, what's integral of f prime? That's what? That's first theorem. Right? So we have two distinct procedures because one is in a value form and the other is in function form. So you have to treat them separately. I think it's easier to do if we can kind of just visualize it as completely separate things. I'm going to separate that 5 from f prime to make it a little bit easier to. So I'm going to separate this and have two distinct procedures for them. We know 3 becomes what? 3x. And then once we have 3x, we can evaluate between our bounds. What happens with f prime? Becomes f of x, and then we can plug in the bounds, right? Okay. Okay, so now it's a lot easier because now you're just trying to get it down to numeric value, but understanding that these are two different procedures because they're presented as two different forms. Okay, so 3 times 13 is 39. 39 minus 6 is 33. And then on the function side, we know f of 13 minus f of 2. We can pull that value from the table of values. We get 6 minus 1. Don't forget about the negative 5. Negative 5 times 5 is negative 25. 33 minus 25 is 8. Okay, last one here, part C. Use left Riemann sum to approximate the depth integral from 2 to 13. Left Riemann sum. Just have to find each of the subintervals here. the width represented by 1, 2, 3, and 5, and then you're going to pull the left y value for each subinterval. Hold on to your negative values. They're not asking for total distance, so you want to keep track of the positive and negative value. Displacement is 18. Okay, so we did part of your homework. So tomorrow I'll check pages 3 through 6. Okay, come get your phones. Okay, appreciate it. Thank you.
On the queue, I think we do this portion of this.
Oh, yeah.
It's after the in 11, so you need two values for that. Yes. And then how do you do that?
It's already positive, so it's actually doesn't matter.
Okay.
Um,
If it was negative, you would just.
you'll make it positive, yeah.
Okay.
Okay.
Oh. Thank you very much. Yeah. Oh, yeah. I'm so upset that execution. I haven't worked so what's that? Yeah. Gives you like a passage of the analyze it. No, we changed it. Yeah. Like, you guys are too good at things. We're gonna give you. So we don't even write about it. We're studying it out.
Okay, thanks.
Told you guys. Why didn't she tell us? Unless she's keeping it for yours, but she told us we're gonna give too. Yeah, that's just fine. There was,
And then, you have 1 and 2 from this packet. Yes.
it's okay, she didn't tell me about the bento box project until yesterday. That one's easy, this is a good session. I really like cheaper about it. It's hard to find my friends. Because of things that it's supposed to see anything that doesn't like see, I think the area is funny, but I seem like it's like it's so like not.
So, let's say, for perfect purposes, let's say that the velocity was
So like
holding.
literally, or the.
Let's say, so let's say velocity was, we know it's more than that. So let's just say that velocity.
Unless your guys is the same, but I
So,
don't.
we know that's the area of the velocity is displacement. And we know this is 24.
Oh, yeah, yeah.
So assuming that the velocity never
It feels
increases,
like
it stays at 3, then
like, I want to do anything about both.
it's equal
Oh, wait,
to
this is probably like-
plus the interval from 0 to 8.
It was so good. So good.
Is equal to
They're all the same.
7
They are.
plus 24.
You just need to make sure you don't use the.
That's if the velocity stays at 3.
In
But we know that's not true, right? We know the velocity is actually,
You have to use like.
he's actually going faster, which means that he's actually covering the ocean. So if we know that his position with this limited, with steady velocity he's already going to reach 31, we know it's going to be more than
Yeah,
31
she was like
because of
saying
the
that.
increased velocity.
Probably like seeing like present some illustrations with something.
Yeah.
Like
Whole other.
a symbol can't illustrate the. Or like it can't like present the being or something. So, it didn't really make sense. It's only 12.